So in microarray, we get some color images, so we need to do their scanning and we need to transform the fluorescence intensity image into a measurement of gene expression for each spot. And image processing for feature extraction affects the quality of the data. As far as those oligonucleotides are concerned, there is an integrated image processing approach, but in case of those pin spotted arrays that have multiple image processing approaches. So in feature extraction, so first we try to extract our features, our spots, our colored spots. So that is where we do the quantitation or quantification of digital images. There are 4 steps involved in that. We identify the positions of the features on the microarray, and for each feature we identify the pixels of the feature or foreground. So feature is foreground, and then we have the background, which may be some signal coming from the glass. And then we identify the background pixels, and then we calculate the intensity of the feature as well as background, and we do some quality control. Here is the overall image. So since our spotting robot has 16 pins, they are arranged into 4 into 4, so total there are 4 rows and 4 columns. And since they spot it in 3 rounds, so each pin here actually is used 3 times, so we'll get a total 48 blocks. So total we have 12 into 4 patterns in our overall slide. If we take what has been spotted by each pin, we have block or grid, so that has 12 into 16 feature spots. So this is how our whole this design looks like. So while we are doing those feature identifications, there might be some problems when identifying the positions of these features. So some features, they might have shifted grid positions. Sometimes you have curves within the grids. You might see some uneven feature spacing. You might have some uneven feature sizes. So softwares are used to determine these properties of these features. So softwares determines which pixels are in the area of the features. We detect fixed size circles. Features may have different sizes. We might have variable circles where we have irregular shapes, and sometimes they report the histograms using the frequency of intensities of the pixels. Now we come with adaptive shapes. From centers they extend to pixels with similar intensity. So these are variable properties which are associated with these features. So background adjustments are there and they are important. So what is the background and what it accounts for is there must be some non-specific hybridizations, some fluorescence coming from the glass. So image quantification is done by image processing softwares. They provide signal or foreground means where we take the mean of the pixels in the features. Background mean represents the mean of the pixels in the background. The same way they give us signal medians and background medians. So sometimes we use means in our calculations, and we might use medians also, where we have the issues like where means are skewed because of some extreme values. Same way those softwares, they provide us the signal standard deviation as well as the background standard deviations. So the structure of a typical data file that is returned by this software, that is .gpr, that is gene pix results file, GPR file. So the images are scanned and the fluorescence intensities are translated into the numbers, and they are returned in the shape of these files that have some rows. Over there we have microarray probes, and columns, they represent informations about those microarray probes, for example locations and intensity values. Typical file looks like this. So first line describes the settings which we are using, date is there, and in the settings we have wavelengths which we are using. Remember that we have said that for CY green cyanine 5, which is dye, so that is using the wavelength that is equal to 635, whereas the CY3 was using the wavelength 532. So they are represented here as 635 and 532. And we have image files. What is the file name where we are saving that? Normalization so far is not done, so that's a raw file. and then in the software with which it was created. So it looks like this. The temperature is also reported. So we have the block information, we have block, column, row, and then we have flags. Remember guys, we have talked earlier about the flags. So they tell us the quality of our features are those dots or spots. So 0 flag is ideal. These features are okay. Negative flags are there where you have more background, there is more noise as compared to the foreground. And same way then you have the intensities where you have CY5 foreground is 500, whereas CY5 background is 40. So 500 out of 40 is comparatively better. If you look into CY3, foreground images signal is 1000, whereas on the background is 50. If you look into this bad feature, that is having the flag of -100, your foreground is 25, background is 20. Again, CY3 foreground is 30 versus 21, so it's kind of a bad feature. Rest of them, they look like fine, where you have the flags of all of them are 0. So this is how it returns you the files. So these 500, 1000, these numbers are actually the intensities of your spots. So you compare the intensities of these two spots. For example, in foreground, for example, you take one sample, you label it with CY5, the other one is CY3. So if you look into this top row, we can see that the expression is higher in case of CY3 as compared to CY5. We can also have those medians. Again, we have block, column, row, and ID of a particular gene, maybe AST1. So we have F635's median, and F stands for foreground, and then we have the background median. Same way we have F532, that is CY3 cyanin 3, the other dye. We have its foreground and background, and then we have the flags. These are some remaining columns. They were not fitting in one slide, so I put it in a separate slide. So it's important to transform the fluorescent intensity signals images obtained after scanning into the measurement of gene expression for each spot, and this image processing is a really important step in microarray data analysis.